Hello everyone, welcome to week 4 learning videos once again. This is learning objective 3. In order to determine which asset allocation decision is optimal for an individual investor, we need to be able to calculate the utility that's derived from complete portfolios. So we mentioned earlier that the strategic asset allocation decision is one where an investor looks at their own personal characteristics and uses that to form an asset allocation in the long run. Here is an example where we have 3 different assets. We are going to call them low, medium, and high risk assets. The low risk assets has an expected return of 7% and a standard deviation of 5%. The medium risk asset has an expected return of 9% and standard deviation of 10%. And the high risk asset has an expected return of 13% and the standard deviation of 20%. Now in this particular case, let's assume that we also have an available risk-free rate of 5%. Now if we are able to decide which of these 3 risky assets would we invest, in the way we might decide is by comparing the Sharpe ratio of each of them. Remembering the Sharpe ratio, the numerator is the risk premium, which is the expected return less the risk-free rate, and the denominator is the standard deviation of returns. So if we compare all these 3 assets, we will actually see that all the 3 assets have exactly the same Sharpe ratio. Therefore, theoretically, the average investor should be indifferent across these 3 assets. So how do we choose between them? Well, what we are going to find is that some of these assets are going to be preferred by a particular group of investors, whereby other risky assets will be preferred by a different group of investors. What determines whether an individual investor will prefer the low, medium, or high risk asset is her personal preferences and, most importantly, her tolerance toward risk. We know that investors, as a rule, tend to be risk averse. So what differs is the degree of risk aversion across investors. Some investors will be far less inclined to take on more risk and hence will be expected to be rewarded with a much higher expected return for each additional unit of risk that they take on. When it comes to calculating the utility that an investor generates from any particular investment, what we find is that utility is calculated as a function of both expected returns and risk, as we've seen previously. But the degree to which changes in risk affect an investor's utility is dependent upon how risk averse an investor is or to what extent they are averse to risk. So basically, we can see from this formula, our utility function or calculation of utility for a complete portfolio, we can see that increasing expected returns increases utility that the investor get from an investment. That makes sense. Simply, we have got a minus sign in front of the variance. Okay, so increase in variance, increase in risk will decrease utility. However, we can see there is one function, additional function here, which is A, which we will be calling as coefficient of risk aversion. You can see that since this variance is multiplied by A, the higher the value of A, the more risk averse investor is. That means the more that every unit increase in risk will decrease the utility. So by now, as a general rule, this A, that means the coefficient of risk aversion, is measured on a scale approximately between 1 to 5. A of 0 will mean that investor is risk neutral, as we know that neutral investors don't actually consider risk. As all this part, for example, if this A is 0, this part will turn to 0, so utility will only depend on expected return. So investor will get higher utility for higher expected return. However, if A was negative, we would actually have a risk lover, and we know that risk lover's utility actually increases when risk increases. But by and large, we expect that majority investors will be risk averse, which is why this will be a positive number, as I mentioned before, somewhere on a scale from 1 to 5. So if we come back to our example before, where we had three assets, we calculate the utility that an investor would get from each of these assets, but we compare here across three different investors. The first investor, as I am going to say, has a coefficient of risk aversion of 2. The second investor might have a coefficient of risk aversion of 3.5, and the third investor might have a coefficient of risk aversion of 5. So applying the formula from before, we can say that for each of these assets, we know that the utility the investor generates is the expected return. So here in this case, for high risk asset, expected return is 13% minus half times A, which in this case is 2. And times the variance of the returns. Okay, if we do that calculation, 13% minus half times 2 times 20% squared, which is the variance, we get a utility of 9%. So what we can do this is, we can also calculate the utility generated by both the low and medium risk asset. We can see that for this particular investor who has coefficient of risk aversion of 2, she has got a very low degree of risk aversion. She is quite willing to take on risk. So utility is maximized when it's a high risk asset. Now let's drop down here and let's compare this to an investor who has a coefficient of risk aversion of 5. For this investor, we can again apply the formula from before. Utility equals expected return minus half A times the variance, or the standard deviation squared. So we can say that expected return times half times 5 and the standard deviation squared, we get three utility values once again. Again, remember, investor will seek to maximize their utility. So for this particular individual, the asset that maximizes utility is the medium risk asset. That's the one that has the highest utility. So we see here three assets that had exactly the same Sharpe ratio, but for two different investors. First had a very low risk aversion and the second had a quite high risk aversion. There were actually different preferences regarding which asset maximizes their utility. We can think of this diagrammatically. We can think of a trade-off between expected returns and standard deviation, and then look at the combination of portfolios where investor would be indifferent. So indifference means that for an individual investor that would be equally happy at any point along this line. As we change our value of A, is that we change our coefficient of risk aversion. As A gets higher, these lines get steeper, which means that for a more risk-averse investor, for every additional unit of risk that they take on, the incremental change in expected returns, or the incremental change in the return that they demand to be indifferent about investing, gets higher. So for a highly risk-averse investor, an investor with A equals 5, that does not necessarily mean that the investor will refuse to invest in high risk asset, but they will only invest in a riskier asset if they are rewarded with a significantly higher expected return for doing so. So the crux of this is that we need to incorporate risk tolerance, or the degree of risk aversion, into the asset allocation decision. So what we are going to do now is we are going to start by assuming an individual investor who has a coefficient of risk aversion and A equal to 4. And let's now return to the example from our previous learning objective, where we had the decision to allocate between a risky portfolio and a risk-free asset. So what we can say for this particular investor is we can consider a range of different asset allocation decision, remembering Y, big proportion invested in our risky portfolio. The balance, 1 minus Y, is invested in the risk-free rate. And one approach we use is we could look at different combinations of Y. We look at the resultant expected returns and standard deviation of the complete portfolio and calculate the utility of this particular investor who has an degree of risk aversion equal to 4. Now we can see here Y increases utility is increasing, getting to some point around 0.086 whereby utility appears to be maximum and then utility starts to decrease with the increase in y. So we can say somewhere over approximately 40% where utility is maximized. If we wanted to plot this utility function across different asset allocations, it looks something like this. And if we plot it for every possible observation, we can see as above, it's roughly around 40% where utility is maximized. However, just saying roughly 40% may not be good enough. What we wanted to be able to is we want to be able to precisely estimate exactly what asset allocation can maximize that utility. And using this manual calculation of calculating utility for different combination is a sort of bit clunky. So we want to do a short here. So to do a shorthand, we think about mathematics and we think about how we can actually calculate a maximum. We know from mathematics that we can calculate a maximum value through differentiation. In order to do this, we come back here. We think about the formulas we had before. We know that the expected return of our complete portfolio was calculated as 1 minus y, which is the proportion invested in risk-free rate, plus the proportion invested in our risky portfolio times the expected return of our risky portfolio. So I can actually rearrange this equation to get the following. This is simply an algebraic recalculation. We know that the variance of our complete portfolio is the weight invested in our risky portfolio squared times the variance of our risky portfolio. We know that because we said before the standard deviation of our complete portfolio is the weight invested in the risky asset times the standard deviation of the risky asset. So we can come down here and we look at our utility function from earlier, and I am going to substitute these values, these expected return values, and the others in the utility function. So by substituting and rearrangement, we get a value of y, the proportion invested in risky portfolio that maximizes utility. So y equals expected return on the risky portfolio minus risk-free rate, or the expected excess return divided by A, that's a coefficient of risk aversion, times the variance of our risky portfolio. So let's go about applying this formula using our information before. So we know, example from before, we had an investor who had a coefficient of risk aversion of 4, and we know that the expected return of our risky portfolio is 15% and the risk-free rate was 7% and standard deviation was 22%. So we substitute this information in the formula y, and we get that the asset allocation that maximizes the utility for this particular investor is investing 41.3% in the risky portfolio. So what we can see that if we change A, optimal asset allocation decision changes. So as we decrease A, investors become less risk averse. They are more inclined to take on risk. Hence, their optimal portfolio has a greater proportion invested in a risky asset. Or if we make the investor more risk averse, we increase A, the proportion invested in the risky asset decreases. So that's how we calculate utility functions and use them to make asset allocation decision. So that's the end of our discussion on learning objective 3. Please watch the next videos for our discussion on subsequent learning objectives. Thank you.